This week's chapter is chapter 5, and it's on Ethernet. With the OSI physical layer provides the means to transport the bits that make up the data link layer frame across the network media. And Ethernet is the predominant LAN technology in the world. So this is the one we're going to focus on for this chapter. Ethernet operates in the data link layer and the physical layer. So that's two layers of the OSI model. The Ethernet protocol standards define many aspects of the network communication, including frame format, frame size, timing, and encoding. When messages are sent between hosts on the Ethernet network, the host formats the messages into the frame layout, and that is specified by the standards. Remember, we have IEEE standards. Frames are also referred to as the protocol data unit, or PDUs, so I may be referring to them in either terminology. Because Ethernet is comprised of standards of those lower layers, it may best be understood in reference to the OSI model, because remember, the TCP/IP model doesn't have as many layers to it. Ethernet specifications support different media, bandwidth, and other layer 1 and 2 variations. The basic frame format and address scheme is the same for all varieties of Ethernet. Ethernet is most widely used, like I said, in LAN technology today. Ethernet operates in the data link layer and the physical layer, and it is a family of networking technologies that the IEEE set up in 802.2 and 802.3 standards. Ethernet supports data bandwidths in 10, 100 megabits. We've got 1000 megabits or 1 gigabit, 10 gigabit, 40 gigabit, and 100 gigabit. As shown in the figure here to our right, Ethernet standards define both the layer 2 protocols and the layer 1 technologies. For layer 2 protocols with the 802 IEEE standards, the Ethernet relies on two separate sublayers of the data link layer to operate: the logical link control and the MAC sublayers. So you see that here in this example. We've got the LLC and the MAC. The LLC is the 802.2, MAC is 802.3. The LLC sublayer, or the logical link control, handles the communication between the upper layers and the lower layers. So you see that it's there between the data link layer and the network layer. It's typically between the networking software and the device hardware. The LLC sublayer takes the network protocol data, which is typically an IPv4 packet, and adds control information to help deliver the packet to the destination node. The LLC is used to communicate with the upper layers of the application, and it transitions the packet to the lower layers for delivery. Also, LLC is implemented in software, and its implementation is independent of the hardware. An example there is in a computer. The LLC can be considered the driver software for the NIC, and the NIC driver is a program that interacts directly with the hardware on the NIC to pass the data between the MAC sublayer and the physical layer. You may have seen on your computer before it says that the driver is missing for a particular device. This is what it is referring to. Also, your MAC sublayer, that constitutes the layer that's lower than the LLC. It's still in the data link layer, and the MAC is implemented by the hardware, typically in the computer NIC. Remember, that's the network interface card. And the specifics are specified in the IEEE 802.3. And here I'm going to switch to figure 2. So we see here our network layer, our LLC sublayer, our 802.2. This is what communicates with the network layer. And here we have the MAC sublayer. So you can see how those interact together. Also, here in this figure, you'll see that the Ethernet MAC sublayer has two primary responsibilities. It handles data encapsulation, that's frame delimiting, addressing, and error detection. It also does the media access control, and what that does there is the control of the frame placement on and off the media, and for media recovery if something should happen. With our data encapsulation, like I said, we have frame delimiting, and that's where framing process provides important delimiters. It identifies a group of bits that make up a frame. The process provides synchronization between the transmitting and the receiving nodes. With addressing, the encapsulation process handles the header that's added to the frame that contains the physical address or the MAC address that enables a frame to be delivered to its destination. And with your error detection, it adds the trailer with a cyclical redundancy check. That way we can make sure that our packets or our frames are getting to their destination. With our media access control, the second responsibility of the MAC sublayer is the media access control, and it's responsible for the placement of the frame on the media and the removal of the frames from the media. So it depends if you are the source or the destination as to which one it does. As its name implies, it controls access to the media, and the sublayer communicates directly with the physical layer. The CSMA process is used to first detect if the media is carrying any signal. So it's looking to see, are you out there? Can I send? This one says, I tried to send when I am ready. This one says, I try to send when I'm ready. And so does this one. And it's looking to see if it's busy or not. When the device is attempting to transmit, it sees that the media is busy, so it holds off. It may wait and try again after a short time period. If no carrier signal is detected, the device transmits its data. It is possible that the CSMA process will fail and two devices will transmit at the same time because they're both listening and they don't hear anything, so they both send out the information at the same time, and then we're going to have a collision. With CSMA collision detection, the device monitors the media for the presence of a data signal. If it's absent, indicating that the media is free, the data is transmitted. And if the signals are then detected that show another device was transmitting at the same time, all devices stop sending and they try again later, and they try at a different sequencing, different time allotment. So we've gone over this before. You need to make sure that you understand the collision detection and collision avoidance so that you get that, because I can guarantee you that you will see that again, probably on an exam. The Ethernet is a multi-access bus, and every network device is connected to the same shared media, and all the nodes receive all frames transmitted. The issue is if all devices are receiving every frame, how can each individual device identify if its intended receiver without the overhead of having to process and de-encapsulate the frame to get to the IP address? It becomes even more problematic on large high traffic networks where there's a lot of frames being forwarded. To prevent the excessive overhead involved in the processing of every frame, a unique identifier called the MAC address was created to identify the actual source and destination nodes within an Ethernet network. Regardless of which variety of Ethernets used, the MAC addressing is provided a method for device identification at the lower level of the OSI model. As you may recall, the MAC address is added as part of your Layer 2 PDU. And the Ethernet MAC address is a 48-bit binary value expressed as 12 hexadecimal digits, or 4 bits per hexadecimal digit. With our MAC address structure, it must be globally unique. The MAC address value is direct result of the IEEE enforcement rules for vendors to ensure globally unique addresses for each Ethernet device. And the rules that are established by IEEE require that any vendor that sells Ethernet devices to register with the IEEE. The IEEE assigns the vendor a 3-byte or 24-bit code called the Organizationally Unique Identifier. Okay, so depending on what company produced that device, it's going to have its own organizational unique identifier. It's 24 bits or 6 hex digits. An example here on the right is showing 0062F, and that tells you that it is a Cisco device. All MAC addresses assigned to a NIC or other Ethernet device must use that vendor assigned OUI as the first 3 bytes. That way you know where it helps make it unique, and then it also helps you identify what your vendor is in case you have issues. The MAC address is often referred to as the burned-in address because historically the address is burned into the ROM or your read-only memory on your NIC, and that means that the address is encoded into the ROM chip permanently. It cannot be changed by the software. There is a side note on this, so remember any side notes are liable to show up on exams as well. On modern PC operating systems and NICs, it is possible to change the MAC address in software. This is useful when attempting to gain access to a network that filters based on the burned-in address. Consequently, filtering or controlling traffic based on the MAC address is no longer as secure as it used to be, because if you can manipulate that code, then it's not as permanent. MAC addresses are assigned to workstations, servers, printers, switches, and routers. Any device that must originate and or receive data on the network. All devices connected to the Ethernet LAN have a MAC address interface, and different hardware and software manufacturers might represent the MAC address in different hexadecimal formats. You'll notice here in the example some have dashes, some have dots, some have colons, but they're all representing the same thing. When the computer starts up, the first thing the NIC does is it copies the MAC address from the ROM into the RAM. Remember, your RAM is your readily accessible memory. It's what's there until you power off. Here's one of those lovely exercises that you can do. You need to practice to make sure you understand where different things fall. Or is it a MAC related issue, or is it an LLC? Ethernet was created in 1973, and the standards have definitely evolved over time. There's a good example here. You can click through and see the different time frames as to what the standards were, what the description of that standard was at that time, and you can see the progression of Ethernet as we go. You also notice up here on the diagram it's showing you that more packets are flowing through the media as we increase our knowledge and our equipment advances. Also here in figure 2 is a comparison of the 802.3 and the Ethernet 2 frame structures and field size. So here we have this information with the field sizes. Both the Ethernet 2 and the IEEE 802.3 standards define the minimum frame size as 64 bytes and the maximum as 1518 bytes. This includes all bytes from the destination MAC address field through the frame check sequence field. The preamble and start frame delimiter fields are not included when describing the size of a frame. Any frame less than 64 bytes in length is considered a collision fragment or runt frame and is automatically discarded by receiving stations. It sees it as not complete. The 802.3 AC standard, released in 1998, extended the maximum allowable frame size to 1522, so it was allowing larger frames to go through. The frame size was increased to accommodate technology called virtual local area networks, or VLANs, And VLANs are created within a switch network and will be presented later in this course. We will get into VLAN switches just a bit. Also, many quality of service or QoS technologies leverage the user priority field to implement various levels of service, such as priority service for voice traffic. You definitely want your phone calls to be smooth so that you can understand, or if you're video conferencing. This figure displays the fields contained in the 802.1q VLAN tag. You can just look at that and see what all's in it, study that a little bit. If the size of a transmitted frame, like I said earlier, is less than the minimum or greater than the maximum, the receiving device is going to drop it because it sees that there's something wrong with it, and it's going to wait until it receives that packet or that frame again. The primary fields in an Ethernet frame are our preamble, and the preamble is 7 bytes, and start frame delimiter, also called the start of the frame, is 1 byte. And fields are used for synchronization between the sending and receiving devices. The first 8 bytes of the frame are used to get the attention of the receiving node. Essentially, the first few bytes tell the receivers to get ready to receive a new frame. So this is the first 8. Your destination MAC address is just that. It's your destination's MAC address. This address is used by layer 2 to assist devices in determining if a frame is addressed to them. If it's not, it moves on to the next device. Next, we have our source MAC address field. This is telling it who it's coming from. Next, we have our length, and that is 2 bytes. And that is from an 802.3 standard earlier in 97. The length field defines the exact length of the frame data field. This is used later as part of the FCS to ensure that the message was received properly. So the length and the frame check sequence works together. Next, we have our data field. Our data field is anywhere from 46 to 1500 bytes. It contains the encapsulated data from the higher levels, which with a generic layer 3 PDU, or more commonly an IPv4 packet. All frames must have at least 64 bytes long, or else it drops it. It sees it is too small. Then we get to our frame check sequence field, and this is used to detect errors in a frame. It uses a cyclical redundancy check, and the sending device includes the result of the cyclical redundancy check in the frame check sequence field of the frame. Again, we have another activity that we can look at. I would work at these if I were you. They will help reinforce what you're learning. You can go through it and try to decide where each thing needs to start, where things need to end, and just, look around, see what you think it needs to have, see where you need to think it goes. You can just drag and drop however you want them to be, and then of course you always check them to see if you have the information correct. The Ethernet MAC. The MAC address is one of the most important aspects of the Ethernet LAN technology, and it uses hexadecimal numbering. If you'll notice to the right, you have an example of how it all works out. Here is a decimal is 0. In binary, a 0 is 0, 0, 0, 0. But in hex, it's 0. 1 in decimal is 1, then binary is 0, 0, 0, 1. Hex is 1. You'll notice that binary starts changing once you hit 2 and 3, and then the hexadecimal numbers change up at 10, and hex goes from 0 to F. So this is some information that you'll need to know. It's important to distinguish hexadecimal values from decimal values. regarding the characters 0 to 9 as shown here in this figure. Hexadecimals is a word that's used both as a noun and an adjective. When used by itself, it's a noun that means number system, and the hexadecimal provides a convenient way to represent binary values. Just as in decimal is based 10 number system and binary is a base 2 number system, hex is a 16 system. Therefore, 0 through F is actually 16 numbers because we count 0 as a number. Given that 8 bits or a byte is a common binary grouping, so binary 00000000 to 11111111 can represent the hexadecimal as the range 00 to FF. Leading zeros are always displayed to complete the 8-bit representation. For example, the binary value of 00001010 is shown in hexadecimal as 0A, because you'll notice that 0000 in hex is 0 and 1010 which is 10 in decimal, is A in hex. It can get a little confusing, but hold on, you'll get there. Hexadecimal is usually represented in text by the value preceded by 0x. For example, 0x73. That tells me that it is a hexadecimal number that I'm looking at. So that should help you some. If you see 0x, you know they're talking hexadecimal. Number conversions between decimal and hex values are straightforward, but quickly dividing or multiplying by 16 is not always convenient. If such conversions are required, it's usually easier to convert the decimal or hexadecimal value to binary than to convert the binary value to either decimal or hexadecimal. You will get there. You will start understanding it. We will work on it. Once we get into subnetting, you will work a lot with binary, not so much with hexadecimal, but this will come with practice. On a Windows host, when you go to your command prompt and you type in ipconfig/all, you see all the information about your Ethernet local area connection adapter. You give a description. It tells you that it's an Intel gigabit network connection. You have your physical address. Okay, this is your MAC address. Then you get more information through here about different parts of the address. Depending on the device and the operating system, you'll see various representations of your MAC address. And this one is using the dashes. And we would use this information to determine who the vendor was for this particular one. Again, you'll see it with dashes, with colons, or with periods between it. If in Ethernet, different MAC addresses are used for layer 2 unicast, broadcast, and multicast communications. A unicast MAC address is the unique address used when a frame is sent from a single transmitting device to a single destination device. So here's an example of the unicast. It goes from here and it goes straight to the server. So it went from, here's our destination MAC address, here's our source MAC address, here's our IP source, here's our destination IP source, IP address, then you have your user data and your trailer. With broadcast, the packet contains destination IP address that has all ones. That says that it's going out to everybody. Okay, so our destination MAC is all F's. That converts to all ones. So we're going to send it out from our source, and the destination is everybody in that grouping. With multicast, the address allows a source device to send a packet to a group of devices, and the device that belongs to a multicast group are assigned a multicast group IP address. The range of the IPv4 multicast address is 224.0.0.0 to 239.255.255.255. Because multicast addresses represent a group of addresses, sometimes called a host group, they can only be used as the destination of a packet. The source will always have a unicast address. And here's an example of that. You will work on this lab. This is viewing network device MAC addresses. This is lab 5.1.3.6. I have a short video for you on that you can view. I placed it in NetSpace just above the Word doc that's available for the lab. There are two binary addresses assigned to a host address. You have your physical address, which is your MAC address, and then you have your logical address, and that is your IP address. Both of these addresses work together to identify a device on the network, and the process of using a MAC address and IP address to find a computer is similar to the process of using a name and address on an individual to send a letter. Okay, so you start out globally large and you start narrowing it down with your MAC and your IP address. It helps your information get to where it's headed. A source device will send a packet based on an IP address, and one of the most common ways a source device determines the IP address of the destination device is through the domain name service, or DNS, in which an IP address is associated to a domain name. For example, Cisco is equal to 209.165.200.225. This IP address will get the packet to the network location of the destination device. It is the IP address that routers will use to determine the best path to reach a destination. Okay, so here's an example of an IP packet encapsulation. So it went from the destination MAC to the source MAC. Then it goes and finds the source IP and destination IP, and then it transfers the data. Here's another example where you can see the devices topology. It's going to go from this device here in Paris. The frame moves across, picks up its different trailer and header informations, and finally ends up in Japan on that device. You'll need to complete lab 5.1.4.3. That is in NetLabs as well. Complete your packet tracer. And all that information is out there for you. I have the Word docs and the packet tracer files out that you're going to need. Next is Address Resolution Protocol, or ARP. And you'll remember that each of our nodes or our devices have an IP address on our network, and both have the MAC address and the IP address assigned to them. In order to send our data, the node must use both of these addresses. It doesn't do them much good if they have the MAC address without the IP address, or vice versa. While the IP address of the destination will be provided by a higher OSI layer, the sending node needs a way to find the MAC address on the destination by a given Ethernet link, and this is the purpose of ARP. ARP relies on certain types of Ethernet broadcast messages and the Ethernet unicast message. It's kind of yelling out there, hey, where are you? And they respond back, here I am, and they give the different devices their IP addresses and their MAC addresses, and then you have a table that is set up that helps with mapping. For a frame to be placed on the LAN media, it must have a destination MAC address. When it's sent to the data link layer to be encapsulated into a frame, the node refers to the table in its memory to find the data link layer address. If it's not there, it looks for them and creates a new link. The ARP table must be maintained, and that is done dynamically by the system. It sends out and looks for the different devices on your network and keeps its table up to date. Okay, let's see the process of how it creates the frame and how it finds the ARP, or it sends out the ARP request when it doesn't know all the information it needs to. Here host A wants to send data to an IP address 10.10.0.3, but it has no ARP entry. So it's never seen anything before, or it hasn't received anything from that device, so it doesn't know exactly where it is. So what it's going to do is it's going to send out its frame or its packet, and it's going to then listen back and see who responds with the information. So host C had that IP address. So now host A has the ARP information for host C in its ARP table. It knows the IP address and MAC address for that device. Then it can send and forward the data directly to host C via the MAC address, and it doesn't take up as much network space and traffic. All frames must be delivered to a node on the local area segment, and if the destination IPv4 host is on the local network, the frame will use the MAC address of the device as the destination MAC address. If the destination IPv4 host is not on the local network, the source node needs to deliver the frame to the router interface that is the gateway or next hop used to reach the destination. So here we have host A again needing to send information out to an IP address, and it has no ARP entry for the default gateway, and we have an IP address of 10.10.0.254. So that's our gateway. So it sends out the information, it hits the router, and the router comes back with its IP address so that the information that host A is sending can go out the router. Periodically, one of your devices may go off the network, and if it tries to send a packet to that device and the information isn't there, that IP address and MAC information will eventually come off your ARP table. On the Cisco router, you're going to do the show IP ARP. This will show you your different ARP table or routing table, and then on your PC you can do ARP space -A, and that's going to show you your table as well. You'll need to complete the ARP table instructions in a packet tracer, and then you also have a lab that you're going to do on that one. The figure to the right shows two potential issues with ARP. You have overhead on the media. As a broadcast frame, an ARP request is received and processed by every device on the local network, so that creates overhead. If everybody's being chatty and sending out their requests, you end up with a lot of overhead. On a typical business network, these broadcasts would probably have minimal impact on the network performance. However, if you get to larger networks, that is going to affect what's going on. Security. In some cases, the use of ARP can lead to potential security risk. ARP spoofing or ARP poisoning is a technique used by an attacker to interject the wrong MAC address association into the network by issuing a fake ARP reply. An attacker forges the MAC address of a device, and then frames can be sent to the wrong destination, so then they're building an ARP table based on your information. Some other ARP issues is that broadcast and security issues that are related to ARP can be mitigated with modern switches. The Cisco switches support several security technologies specifically designed to mitigate Ethernet issues related to broadcast in general and ARP in particular. Switches provide segmentation of our LANs, dividing the LANs into independent collision domains. So it keeps our traffic separated, it keeps our collisions separated, and it helps with the overhead. With our LAN switching, you'll recall that the local topology of an Ethernet network is a multi-access bus in which devices all share access to the same medium. With the logical topology determines how hosts on the network view and process frames sent and received on the network. However, the physical topology of most Ethernet networks today use something that looks more like a star or an extended star network, and this means that most Ethernet networks in devices are typically connected in a point-to-point basis or to a layer 2 switch. The layer 2 switch performs switching and filtering based only on the OSI data link layer or the layer 2 MAC address. A switch is completely transparent to network protocols, so it doesn't really care which protocol you're using as far as the switch is concerned, and user application. A layer 2 switch builds your MAC address table that it uses to make forwarding decisions. Also, with layer 2 switches, they depend on the routers to pass data between independent IP subnets, and we'll get to IP subnets in a couple of chapters. Here you can practice seeing if I send something from H1 to H6, click send, you'll see how this affects your MAC table, or how it looks into your MAC table and gets to the destination. So you can practice this. Let's see how things go. So practice with that till you get a good understanding of how the switching works. Switches use MAC addresses, like I said, to direct network communications through their switch fabric to the appropriate port toward the destination node. Your switch has its MAC tables built in, or it has established them through the different traffic that's been going on. Your switch is going to determine how to handle incoming data frames by using the MAC address table, and it builds its MAC address table by recording the MAC addresses of nodes connected to each of its ports. Once a MAC address for a specific node on a specific port is recorded in the address table, the switch then knows to send traffic destined to that specific node out that port. It's not looking around for it anymore. So an example here to the right is if the switch receives a broadcast from PC1 on port 1, then the switch enters the source MAC address and the switch port that received that information into its MAC table. And right now you see that port 2 and port 3 have empty entries. Then it sends out the broadcast. It receives information back from port 3. It adds that to its MAC table and sends it on to PC1. If the information had been destined for PC2, PC2 would have replied and port 2's information would have been filled. With switching, we have what's called duplex settings. You can have half duplex settings, and that's where communications rely on unidirectional data flow, where sending and receiving data are not performed at the same time. So it either sends or it receives, but it doesn't do both. There's higher potential for collision, and you have hub connectivity. With full duplex, you have point-to-point only. It's attached to a dedicated switched port. It requires full duplex support on both ends. It's collision free, and it's running collision detected circuits are disabled, and your information can flow in both directions at the same time. That's why it's full. In addition to having the correct duplex settings, it's also necessary to have the correct cable type defined for each port. Connections between specific devices, such as switch to switch or switch to router, and switch to host and router to host devices once required the use of specific cable types, crossover or straight through. Today, instead, most switch devices now support MDIX auto interface configuration, and that's where the device itself knows which type of cable. If you should put a straight through cable in, it can flip the signals into a crossover. So it's not as important on newer equipment. If you're running legacy equipment, you do need to know whether or not you need to have crossover or straight through cabling. In the past, switches used one of the following forwarding methods for switching data between network ports. You either had store and forward switching or cut through. Your store and forward switches receive the entire frame and computes the CRC. And the CRC is the cyclical redundancy check. And if that's valid, the switch looks up the destination address, which determines the outgoing interface. And then the frame is then forwarded out the correct port. With cut through, the switch forwards the frame before it's entirely received. At a minimum, the destination address of the frame must be read before the frame can be forwarded. God, who else would it know to send it to? Here's an example of store and forward information for the switching. In cut-through switching, the switch acts upon the data as soon as it's received, even if the transmission is not complete. So we just saw how in the straight-through it went and looked and got all the information before it sent it to its destination. Now let's watch what cut-through does. Here you have your activities to see if you understand the store and forward or the cut through. And here is yet another activity. Again, I highly suggest that you work on these activities to make sure you've got a good understanding of what the different ones are going to represent. You need to know the store and forward and the cut through switching. A switch analyzes some or all the packet before it's forwarded to its destination host, and the switch may use a buffering technique to store frames before forwarding them. Buffering may also be used when the destination port is busy due to congestion, and the switch stores the frame until it can be transmitted. You have port-based memory buffering and shared memory buffering. Your port-based memory buffering or frames are stored in queues that are linked to specific incoming and outgoing ports. Your shared memory buffering deposits all frames into a common memory buffer, which all the ports on the switch share. So that's some of the main differences between those. Here's another activity for you to work on to determine how the switch forwards a packet based on the source MAC address and the destination MAC address and information in the switch MAC table. You will complete the lab using the iOS command line interface with the switch MAC address. Next we have the fixed or modular. What we're talking about there is when you're selecting a switch, it's important to understand the key features of the switch options available. This means that it's necessary to decide on features such as whether power over Ethernet is needed, and the preferred forwarding rate. As shown in Figure 1, Power over Ethernet allows a switch to deliver power to a device, such as your IP phones and some wireless access points, over your existing Ethernet cable. The forwarding rate defines the processing capabilities of a switch by rating how much data the switch can process per second. Your entry layer switches have lower forwarding rates than your enterprise layer switches, basically because of the amount of traffic they typically handle. You're not necessarily going to have an enterprise layer switch in your home, but an entry layer switch, if you had one in your home, should suffice. There are options sometimes referred to as switched form factors. You have a fixed configuration switches, and they're just as you might expect. They're fixed in their configuration. You don't go in and change them up. Modular switches you can switch up, and depends on what you put in them. You can have a 24 port line card, or you can switch that out for a 48 port line card. Here in Figure 1 you see the Power over Ethernet, and here in Figure 2 you have your fixed configuration. When you come to the labs to actually do Labs Live, we have the fixed configuration switches. Here's an example of modular configuration switches, and then you also have stackable configuration switches. Your Cisco switch product lines are widely deployed globally. You have different options that you can go into for your switches. Here is the Cisco optical gigabit Ethernet. You have a Cisco 100 base T copper, and then here you have a 2-channel. Depends on what it is that you're needing and what your money can afford. Can get very pricey. With layer 3 switching, they're capable of performing your layer 3 routing functions. They reduce the need for dedicated routers on a LAN, and layer 3 switches have specialized switching hardware. They can typically route data as quickly as they can switch it. Layer 3 switch is able to direct traffic throughout your network based on your IP information. You're typically also not going to have a layer 3 switch in your home. It's more into a business experience. Layer 3 switching. With Cisco devices which support your layer 3 switching, they utilize something called Cisco Express Forwarding. The forwarding method is very complex, but fortunately that takes place in the background. It's kind of behind the scenes. Normally very little Cisco Express Forwarding or CEF configuration is required on a Cisco device. Basically, it decouples the usual strict interdependence between layer 2 and layer 3 decision making, and what makes forwarding IP packets slow is the constant referencing back and forth between layers 2 and layer 3. So to the extent that layer 2 and level 3 data structures can be decoupled, forwarding is accelerated. The two main components of Cisco Express Forwarding operations are the forwarding information base and the adjacency tables. It likes to see who its neighbors are. With the forwarding information base is conceptually similar to a routing table, and the router uses the routing table to determine the best path to the destination network based on the network portion of the destination IP address. With CEF, information previously stored in the route cache is instead stored in several data structures for CEF switching, and the data structures provide optimized lookup for efficient packet forwarding. A network device uses FIB lookup table to make destination-based switching decisions without having to access the route cache. The FIB is updated when changes occur in the network and contains all routes known at that time. With adjacency tables, it maintains the layer 2 next hop address for the FIB entries. The separation of the reachability information and the forwarding information provides a number of benefits, and they are that the adjacency table can be built separately from the FIB table, allowing both to be built without any packets being process switched. And the MAC header rewrite used to forward a packet is not stored in cache entries, so changes in the MAC header rewrite string do not require invalidation of cache entries. So Cisco networking devices support a number of distinct types of layer 3 interfaces. We have our switched virtual interface. That's the logical interface on a switch associated with a virtual local area network, or the VLANs that we mentioned earlier. We have routed post. Those are the routed port. That's the physical port on a layer 3 switch configured to act as a router port. And then we have our layer 3 ether channel, and that's a logical interface on a Cisco device associated with a bundle of routed ports. Routed ports enable Cisco switches to effectively serve as routers, and each port on such a switch can be configured as a port with an independent IP network. Our layer 3 ether channels are used to bundle layer 3 ether links between Cisco devices in order to aggregate bandwidth, typically on uplinks. Here's one of those notes, so keep this in mind. In addition to SVIs and layer 3 ether channels, other logical interfaces on Cisco devices include loopback interfaces and tunnel interfaces. In order to configure your switches, some of the commands you're going to need to know. On this one, we're going to look at the interface FA06. You're going to tell it that it's no switch port. You're going to give an IP address and no shutdown. So we see when we do an IP interface brief, here's our interface that we just configured. Here's its IP address, and it's in an up state. The no shutdown brings it into a up state. You'll complete the packet tracer on configuring layer 3 switches. If you have any questions on the information that's covered in Chapter 5, please send me a message through NetSpace, and I'll get back to you on that. And I will have Chapter 6 activated next week. Thank you.